But now it is my pleasure to introduce today's first speaker, Dr. Kanishk Jain. Kanishk completed his bachelor's degree at the University of Virginia before moving to UCLA for his PhD in Stephen Clark's lab, where he studied the PRMT methyltransferase. He then moved to UNC Chapel Hill to join the lab of Brian Strahl for his postdoc. There he's done some really cool work characterizing histone PTM reader proteins, particularly those PHD fingers. His recent work uncovers the importance of nucleosome histone tail dynamics for engagement by readers, writers, and erasers. He's also received several awards and grants, most notably the American Cancer Society Postdoctoral Fellowship. He's also soon to be on the job market, so reach out to him if you want him to apply to your department. I'm sure that any department would be lucky to have him. But for today, I'm very excited to hear his talk on acetylation-mediated histone tail accessibility governs the read-write mechanism of H3K4 methylation. So please join me in giving a warm, albeit virtual, welcome to today's first speaker, Kanishk Jain.
All right, thanks, Ben, and thank you for having me. I'm just going to make this a little smaller here. Sorry, I don't know why my mouse is lagging, so that's perfect. All right, it's fine. Thanks for the introduction, and I am very excited to talk to you guys about my primarily biochemical and some cellular work on figuring out the dynamics between histone tails on nucleosomes and how that impacts H3K4 methylation. So this field and this group of people doesn't need much of an introduction about what nucleosomes are. So I won't go into too much detail there, but suffice it to say that we are understanding over the last few years that histone tails on nucleosomes are not necessarily rigid structures. And in fact, our canonical understanding of nucleosomes as being these extended protrusions from the nucleosomal core is perhaps a little misguided. Over the last couple of years, including this wonderful paper by Emma Morrison, I think she gave a talk in the seminar series last year, they showed via nucleosomal NMR that in fact nucleosome tails, which are highly positively charged, exhibit this conformational dynamics between an autoinhibited state and an accessible state. So in this scenario, the positively charged nucleosome tails are collapsed onto the negatively charged nucleosomal DNA, and that equilibrium exists between a collapsed and an extended state. And it is in this extended state that proteins such as reader domains, in this paper, they look particularly at the PHD of BBTF, are able to access the N-terminal tails of these histones. And because in this diagram, the equilibrium between the autoinhibited and accessible state is shifted towards the inhibited form, it is difficult for proteins to read and access these N-terminal tails. However, what Emma found in this study was that when these tails are acetylated, here the green marks, then you remove some of that positive charge on the lysines and actually make the equilibrium shift towards the accessible state such that more reading and more accessibility can be gained by reader domains to their N-terminal tail on nucleosomes. So the first part of the work I will be talking about to you today has to do with just confirming that this holds true not just for the PHD region of BPTF, but other reader proteins. And so we did this in collaboration with Epicipher, which is a company out here in the Research Triangle Park, and some of you may be familiar with them. So primarily we have a host of histone reader proteins that can be immobilized on beads, as well as having other beads that have nucleosomes with different modifications immobilized. And then you basically do a sort of a fancy FRET assay, Alphascreen binding assay, to determine how these nucleosomes and reader proteins engage with each other and what the effect of those modifications is on the binding events. And so in our case, we looked at 3 specific reader regions, PHD regions from K7A, DIDO1, and MLL5. All three are well studied and have been shown to bind H3K4 trimethylation. And when we look at their interactions with differentially modified histone peptides, here you're seeing various H3 lysine modifications. We see that they primarily interact with H3K4 methyl species of peptides, and then they also similarly interact with those same K4 trimethyl species that are also triply acetylated downstream, meaning on K9, 14, and 18. What's important to see here is that a lot of these reader proteins don't really show a preference between the methyl states of K4, and that even when K4 methylated peptide is acetylated, there isn't much of a difference between the binding signal we see here and here. However, when you use the same modifications but on nucleosomes, the binding is significantly narrowed. And in fact, here we see that H3 acylation in general shows higher binding affinity towards the K4 trimethylated region that these PHD readers are supposed to be binding. So almost all of the binding to just the methylated regions of the nucleosomes is gone. There's some, but it is significantly higher when those tails are also acetylated in cis on the same tail. So the NMR studies from Emma Morrison looking at BPTF hold with other proteins as well. But in addition to histone PTM readers, we wanted to ask whether histone PTM writers are governed by the same H3 acetylation switch. And to look at this, we studied a particular H3K4 methyltransferase. And here we're looking at MLL1 or KMT2A and the MLL1 complex, which you see the cryo-EM structure of here and the different proteins that it is comprised of here. And so we purified these different proteins, assembled the MLL1 complex, and then just did classical tritiated SAM methyltransferase assays on nucleosomes. And much like the reader domain assays, we found that acetylation has a significant effect on methylation activity exhibited by MLL1. And so what we're seeing is a whole host of nucleosomes here, either unacetylated or acetylated in the context of having a 0, 1, 2, or 3 methyl state of K4 on H3. And we see that every time the cognate nucleosome is also acetylated, you get significantly higher methylation activity exhibited by MLL1. And of course, as you provide MLL1 with already methylated species, you're going to get lower activity in general because fewer actual methylation events, detectable methylation events are occurring. Now, this is all at a single substrate concentration, a single nucleosome concentration. So over a titration of nucleosome concentrations, i.e. doing steady state kinetics, pretty old school enzymology, we found the same thing to hold true at all concentrations tested. So again, I'm highlighting for you just the H3K4 unmodified plus K9, 14, 18 acetylated nucleosomes versus just the H3 unmodified nucleosome. So in essence, just a completely unmodified nucleosome in the brown, I guess, here, and, or sorry, in the black down there. And we see that at all concentrations, there is significantly more methylation occurring on the acetylated nucleosomes. So, you know, this holds true at all concentrations. And in fact, the kinetic parameters of this work out in such a way that we see while the catalytic efficiency of the enzyme is affected by this acetylation, the binding affinities are not. So it's not like the acetylation is somehow causing a different binding event to occur between the nucleosome and the MLL1 complex such that you get higher activity. There's just overall higher activity, and I'll get into why that may be happening in a little bit. And again, it's just very important to understand that all of these modifications are in cis. So we're looking at H3K4 methylation on the same tail as the acetylation marks. And that's important to understand here. What's also interesting is that if there are some old school biochemists here, they might notice that the fit to these curves is not exactly hyperbolic. It is a sigmoidal curve. So these data are fit to the Hill equation, which is used when you suspect there's positive cooperativity, allostery. And the reason I did this is because using the classical Michaelis-Menten equation that most enzymologists use, when there isn't positive cooperativity, we were not getting a good fit at lower substrate concentrations. And in fact, you see this regardless of whether H3 is unmodified or acetylated. And there's very few studies in literature right now that are looking at the enzymology of K4 methylation on nucleosomes, but the ones that I have seen so far, such as this structure paper that came out in 2019, looking at H2B ubiquitination and MLL1 activity, they fit this unmodified nucleosome core particle to the Michaelis-Menten equation, but one can see that the fit is not great, right? So I think there is reason to believe that this phenomenon is occurring on all types of nucleosomes, between all types of nucleosomes and the MLL1 complex. Both of these complexes, the nucleosome being one and the MLL1 complex being the other, are large complexes that are going to have multiple points of contact with each other. And so it stands to reason that there is potential for positive cooperativity. And that's another avenue that I think needs to be studied more carefully. So, okay, this is all in vitro in tubes, and we've put in a bunch of proteins and looked at the outcome with regard to methylation and binding. But does this reading and writing acetylation switch for for H3K4 methylation happen in cells? Does that happen in our cells? The short answer is yes. So this work was in collaboration with Dr. Nicholas Young from Baylor College of Medicine. And we did middle down mass spectrometry on MCF7 breast cancer cells to look at H3K4 methylation levels on the same proteoforms as acetylation occurring. Okay, and I'll explain what proteoforms means. Proteoforms are essentially just the same exact molecule when you're detecting methylated and acetylated species in a mass spectrometer. So the way we did this was by boosting acetylation levels artificially by treating with sodium butyrate, which is an HDAC inhibitor, so a histone deacetylase inhibitor. In untreated cells, we have, we're looking at different methyl states. Each color is a methyl state of H3K4 that also has at least either none, 1, 2, 3, 4, or 5 acetyl marks on the same molecule, on the same proteoform. And in untreated cells, the statistics are hard to say whether there's a difference between the high-ordered acetylation and the high-ordered methylation states correlating together, just because in untreated cells, there is very low levels of highly methylated H3K4 in general. We don't normally have H3K4 trimethylation on all the time, ubiquitously. So this is one of the reasons, technical reasons, why we also treated with butyrate, because that not only boosted the levels of acetylation in the cell, but we are now able to see in a more clean fashion the relationship between high-ordered acetylation and high-ordered K4 methylation. So for the interest of clarity, we're not showing all of the statistically significant comparisons, but if you just look at the H3K4 methylation levels, each of these guys is significantly increased with respect to no acetylation in each of these higher ordered acetylation cases. So essentially what this boils down to is in this penta-acetylated proteoform of H3, you have the highest accumulation of H3K4 trimethylation as well. And one can resolve this over time as well. So, by taking time points of butyrate treatment, we see that the H3K4 trimethylation levels increase robustly within 30 minutes to 60 minutes in the penta-acetylated state. So all of this is to say that for almost 2 decades now, we have been thinking about H3 acetylation and H3K4 trimethylation, methylation in general, as these concurrent gene activating marks. And we've seen, this is one of the earliest pieces of evidence that was shown in 2007 or 2006 in PNAS from Dave Alice's lab that shows the occurrence of K4 trimethylation with H3 acetylation in tetrahymena. So this wasn't even in humans, just in tetrahymena, right? And what our work goes to show is that biochemically there is a sort of sequence of events that happens. And so the way I think this works is that the MLL1 complex itself is able to sit on these nucleosomes and stay there without any acetylation, and the tails are all collapsed onto the nucleosome core. But because they're collapsed, the active site doesn't have any access to the H3K4 residue itself. And so there's low levels of methylation. However, when those tails are acetylated, you get expansion or release of the H3 tail. And now there is a lot more available substrate so that the ML1 complex can methylate H3K4 in a more robust manner. And you get an increase in H3K4 methylation overall. So there's still a lot of remaining questions that we're trying to address at the moment. Namely, most of the stuff I showed you is just biochemical observations. And so we want to see how H3 acetylation and methylation affect transcription individually. If you decouple acetylation and methylation, what happens to, say, the transcriptional profile in cells by doing RNA-seq. We also want to see whether the co-occurrence of H3K4 methylation has a preference for certain residues, right? In vitro, we just looked at K9, 14, 18 acetylation at the same time. But what about individually at K9, 14, or 18, or even 23, 27, and 36? So that's ongoing, and I can show you some data on that if there's time or if someone has a question about it. And also, what about other writers and erasers? What about other methyltransferases? What about other demethylases? What about other phosphorylation? About other kinases, right? So that is also ongoing. There's a great first-year grad student in our lab, Jeff Fox, who is starting to look at these things, and hopefully we'll have some cool answers on that front by the end of the year. That's the beauty of biochemistry, I guess. And can such effects be tuned? In the complex environment that is the epigenetic landscape, there's multiple kinds of modifications on these tails. So what flavor of modifications give us, desirable H3K4 methylation levels, and how do we control that? So with that, I'll just acknowledge my funding sources from the NCI, UNC, American Cancer Society, and also acknowledge the members of my lab and our collaborations from the Young and Cosgrove Lab and Epicipher. And thank you for listening.
Awesome. Thank you, Kanishk. That was such a great talk. We've got a couple raised hands, and I have one quick question first, which is, I was really struck by the magnitude of effect on MLL1 activity you see with acetylation.
Yeah.
I was wondering, have you thought much about how cellular processes that might similarly affect histone tail dynamics, such as RNA pull-to elongation, might also impact the enzymatic activity of histone modifying enzymes?
Yeah, that's a great question. And I think, so with pull-to elongation, the modifications that come to mind are things like K36, trimethylation, right? And we're looking at SETD2 activity as well in this context. I think in a more complex environment, one might think about doing in vitro transcription or something to look at that. That's a little bit more complicated. But yeah, that behooves studying for sure.
Yeah. I mean, in the Adolin lab, we always think about pull-to pausing and how having pull-to sitting there at the start where you have all these modifications and how this might interplay.
Yeah.
But let's get to some of the raised hands, not just me. So Bronwyn has her rate. I'm going to click allow to talk. You should be able to unmute yourself and ask your question. Okay, maybe while Bronwyn's figuring that out, we'll move on to Ben Weekly. So I'll let Ben talk. Or unless Bronwyn, are you there now? No, she's gone. Okay, Ben, go ahead.
Sorry, I accidentally raised my hand. I didn't mean to. Great talk, though. Thank you.
Hi, can you hear me?
Yes.
Awesome. Great talk. Really enjoyed it. I was curious. So work by Catherine Musselman and others have shown that acetylation of H4 can also enhance the H3 tail acetylation. So have you guys considered looking at this in the context of these nucleosomes? Because I was wondering if that would maybe lead to a more Michaelis-Menten type kinetics.
Yeah, I am curious about that, especially since the one thing we've studied in great detail right now, right, is this large MLL1 complex. But I'm curious to see if other enzymes that aren't complexed behave the same way, especially with H4. Things we're considering are looking at PRMTs that, you know, heavily, but they're a little bit more promiscuous than lysine methyltransferases, so that it's hard to do in vitro. But yeah, H4 is also another area for us to look at that we're interested in for sure.
Great, thanks.
And then maybe one last question in the chat from Peter, who says, do you think this mechanism impacts all members within the MLL family? Does acetylation co-occur with H2B ubiquitin?
Also a great question. We're actually looking at KMT2D right now, which I was going to say MLL4, but I never know if it's MLL4 or 2 anymore. So I'm just going to say KMT2D. And whether these phenomenon co-occur with H2B ubiquitination, we kind of want to look at it biochemically first, and it's hard to get those nucleosomes made. So that's kind of a technical challenge, but we do have a ton of mass spec data available to us that we're going to be mining through to get at that question as well. Thank you.
Okay, we're going to wrap it up there. There's another question in the Q&A about demethylation, and you can maybe just type your answer there. But let's end it there for time. And so thank you again for the fantastic talk.